Ready. So hi, and my name is Roger Marks, and I'm a newcomer. It's my first NANOG meeting, so I'm going to just take a little time to introduce myself. I spent 17 years working for NIST in Boulder, Colorado, and then I left there and did some other things, and currently I'm a consultant working for some companies and developing some of my own technologies. And most of my activity now is focused on work that I do within IEEE 802, which is the Landman Standards Committee that develops standards for layer 1 and layer 2. I've been happy to hear that that's a topic of interest here. I've heard lots of discussion this week about issues in the 802.1 working group, where we do standards for bridging and time-sensitive networking, for example. The 802.3 working group that develops the Ethernet standards. 802.11 working group develops the wireless LAN standards, and some other things that show up. So I work across the board. Currently, I'm the vice chair of the IEEE 802 Executive Committee, so I get a chance to see things that are happening throughout the organization, and I work technically throughout some of the working groups as well. Before my consulting period, I spent some time working with the so-called WiMAX forum, which was supporting the IEEE 802.16 standard that I spent many years chairing, that developed this technology that was popular for a while called WiMAX. And one of the things that happened when I worked in that forum is one of my colleagues was Edward McNair, who's currently the executive director of NANOG, and obviously doing a great job here. So I do want to thank Edward for suggesting that I bring this topic to NANOG and discuss it. And just the last little piece there, I'd like to say that I'm really having a great time here, and thanks to everybody for being friendly. It seems like a great organization and a good place to work in. I've become a member, and I hope to be back. So with that all said, as an introduction, one of the things that I do in 802 is I chair a group called Nendica, and I'll tell you about that. And we have been doing some work related to data center networks, and I wanted to introduce it to you, but also talk about how we might engage with you folks and with a NANOG interest. This talk was actually not from me, but from Nendica as a whole, and it was approved by the organization. And IEEE wants me to make sure that you know that if I present information on IEEE standards, I'm speaking on my own behalf, and that's my personal view. And nevertheless, the slides were adopted by the organization. So Nendica is a kind of a new thing that's supported within IEEE called an Industry Connections Activity. And Nendica stands for the Network Enhancements for the Next Decade Industry Connections Activity. So we don't actually develop standards, but we try to look out to see what might be coming in the future that would influence requirements that would stimulate standardization that we could do that would be helpful to the user community. One important thing about Nendica is that the way we operate is we don't have any membership, so anybody that wants to participate is entitled to do so on an equal basis with everybody else, and we don't do any membership tracking, so that makes it a good organization to work with other organizations. These industry connections activities, according to the IEEE Standards Association, provide an efficient environment for building consensus and developing many different types of shared results. And we don't develop standards, but we do things that could be precursors to standards. In the specific case of Nendica, we're supposed to assess emerging requirements for IEEE 802 wireless and higher layer communication infrastructures, looking for gaps and trends that are not currently addressed, and facilitate building industry consensus toward proposals to initiate new standards development efforts. And one of the things that we focus on is enhancements that will focus on vertical networks and also enhance cooperative functionality among the existing 802 standards to support network integration. So during the 2 years we've been in existence, We've identified two specific areas where we've gotten work done because the participants have brought forward some ideas where they thought we needed to do some new work. And one of them I'm going to focus on today. It's a lossless network for data centers. Paul Congdon was the editor of that activity, and we published a report, which you can find on our website. It was published last August. And our reports, when they're published, they include an invitation to comment on the report and the process for you to submit comments that we'll consider. That means that we're thinking about it as an ongoing activity, and we're open to doing revisions to these reports. And I think we're probably soon going to start an activity to revise this. And I'll tell you a little bit about one of the specific standardization project that spun off of this called 802.1 QCZ on congestion isolation. A second topic that I'm not going to go into today is on flexible factory IoT that has a significant focus on wireless in the factory, and we have a draft report under development. So getting back to the data center work, we list in the report some of the key messages that we have about that we wanted to convey in this report is that packet loss leads to large delay and congestion leads to packet loss. There are some conventional methods to deal with those, but they're problematic. Even in a layer 3 network, we can take action at layer 2 to reduce congestion and thereby loss. I'd just like to add that we've had some discussions with other organizations, including interaction with IETF. We did a workshop together with IETF last November in Bangkok on this specific topic, and it was interesting to see that the perspective from a lot of the folks in IETF was that they didn't realize that anything in IEEE would be relevant to data center networks because they thought of them as being focused on layer 3, but they came to understand that the kind of work we do in 802, and I'll talk about today, could support what they're doing, even though it takes place below layer 3. And the work, even though we use the word lossless in the title, we're not specifying a lossless network, but we're providing methods to progress toward a lossless data center network in the future. In the report, which I hope you'll take a look at and see if it's helpful to you, we talk about some of the use cases for data center networks and online data intensive services, deep learning, non-volatile memory, express, and cloudification of the central office. And we tried to extract the commonality, and the overall theme there is a dependence on the parallel computation that goes on in the network and how that affects the networking within the data center. So this figure is taken from the report. It's pointing out that the applications are distributed and they're latency sensitive. And this is basically showing the idea of something that you could think of as a web search where a request comes into an aggregator with a deadline to respond, and the request has to be distributed to some further aggregators and then eventually to some worker servers or VMs or whatever containers they may be on a very short deadline because the results will have to be brought back together. And one of the results of that is when all this information is coming in, when the network has to bring data in from many different sources into one central aggregation as it goes back up, as this information that's collected at the bottom of this figure goes back up to the top. It's all coming together at the aggregator and resulting in an incast circumstance that can lead to packet loss and retransmission, more congestion, and more delay. I think in many cases the networks are set up so that they don't, if data is not back by a certain amount of time, it times out and it lives without that data, but that can be harmful to the results. So we just have a few figures here to illustrate the kind of thing that we're looking at. This figure looks a little bit like the one we saw in the last talk. You can see that in a folded class network, you have many paths to get from server to server, and we're just showing one path in blue. And the popular approaches, and you see in this kind of network is something like ECMP, where you assign a flow to a path at a kind of a quasi-random basis, and two flows by chance are probably going to be going to different routes and be less likely to hit each other, but also distribute the traffic across the network. One of the problems you have when you do ECMP is that you can have, just by chance, you can have a couple of large flows that may collide, end up being sent through a same switch and lead to some congestion that can be hard to manage. Another problem, to try to illustrate the incast problem, is shown here, where you have two flows, a green flow and a blue flow, and they because it's incast and services are collecting data from multiple places into the same point. I'll just point to the screen on the left. You can see that these flows are coming together, and they're piling up in an output queue that's going out to some server. And in this kind of environment, you get congestion at the output queue that's not a result of the route that was taken. So ECMP can't help, because all these flows, no matter what routes they take, they're all going to eventually result in a busy output port. Now, IEEE 802 has a history in this area. There's 802.1 working group had a data center bridging task group for a number of years, and one of the standards they developed was originally called 802.1 QBB, which specified priority flow control, and that's still in the standard, in the 802.1Q standard. And the basic idea is that, let me just step back a little bit before that. An earlier kind of concept in 802.3 was the idea of a pause frame, and if a queue got too busy, a device could send to the switch a pause frame and say, just hold on a second until my queue empties out a little bit. And that's a very crude hammer, because it stops all the traffic coming in from that link. So PFC was designed to be a more subtle way to pause traffic, and it was priority-based. And you have in 802.1Q, you have these 8 different QoS classes, and in many cases, you may have different queues for each traffic class. And so if you've got a busy scenario here showing on the output queue, where you have greens and blues filling up the output queues, and then as a result of that, the input queues are going to start to fill, let's say with this blue traffic. And the PFC lets a message be sent from this switch to this switch saying, hold on a second, we need you to pause for a while this particular traffic class. You don't have to pause the other ones, but this particular one, hold on to, because we're getting filled. And that was a useful idea. It has been deployed. It's not unheard of in environments, so people have had some difficulties with it. It has some limitations. And one of the problems we're concerned about here is the fact that stopping a traffic class is still a fairly crude hammer, because there could be other traffic of the same traffic class that's not part of the congestion problem. And for variety, I'm going to point to this screen. So this is showing that, see, here's a green flow and a blue flow that are combining at some output port to result in incast. But there may be a magenta flow that is coming from a different server and coming out a different port, and really has nothing to do with the congestion. But it's of the same traffic class, and so if you freeze this particular traffic class, you're going to freeze this victim flow, and the data is not going to be able to flow, even though it's really not necessary to do so for any particular good reason. It's just that it happens to overlap the traffic class. So that's one of the things that we're trying to deal with in this activity. We identified in this report, and as a result of the report, we did start up a new standardization activity, this 802.1QCZ, that's looking at congestion flow isolation and trying to more subtly deal with this problem of congestion. And we try to illustrate here in this figure with four states. And this is showing like an upstream switch and a downstream switch. And we have some traffic that starts to build up in an output queue. That's this little red burst saying, hey, this queue is starting to fill. And what we do is, if we can identify the flow that's causing this difficulty, we put it off in a separate queue, and we start stacking up those packets in a separate queue and take them out of the filled queue and let that queue continue to process, including these victim flows can go ahead and be processed. And that'll start to fill. Eventually, if it's very slow, then maybe the input queue starts to fill, and there's a point where we can send a message back, what's identified as a CIP message back to the next stream saying, hey, we're starting to even fill up the queues that are available for this traffic, and can you do the same thing upstream, put that into a separate stack. And if it gets really stacked up, we have the ability to send a PFC to take a bigger hammer to the problem. I put in a couple of figures here that illustrate the same idea in a more detailed way. And these figures were taken not from a Nendica output, but from a Nendica input. We just a couple of weeks ago received this interesting document. I think it's interesting. Here's a document number. You can find it on our website. And it's a contribution that came in from a university that was looking at some of the proposals that we had made here and trying to analyze what happens. And this gives you a more detailed example of how this kind of congestion isolation will work. And what you'll see, this is showing the congested case, and they're looking at a very simple analysis in a kind of a steady state. And they're showing that this red are congested flows, and then here's a port where you have a kind of a mixture of the congested flow and this non-congested, the yellow one. And it's showing that if you simply look at in the steady state based on priority flow control issues that you issue, then you're getting about these two non-congested flows, the yellow and the blue, are getting about 33% of the capacity that's getting through to the destination. And then it's saying saying that if you can have a separate queue for this this congested traffic, that you can get these victim flows up to 66% throughput without and maintain the 100% flow to the congested flow. So I think that it's worth looking at this if you're interested in this problem. I think these figures are pretty helpful, and there's also the paper that is the source of these two figures that you might want to refer to. Another common approach to this kind of problem is to do explicit congestion notification. There's many forms of this. There's layer 3 and there's layer 2 forms, but essentially if you get congestion, there's a possibility of doing feedback back to the source and trying to send a message back to the source saying, hey, we've got a blockage here and you need to hold back there. But that involves control loops that the timing is a little bit tricky, and it's a little hard to understand and analyze that, how that might work in all possible scenarios, but that's certainly something that's used in these cases. If you look in the report that I've been mentioning, we mention a few other topics in less detail, but they're ones that were raised in terms of the discussion as to issues that could be relevant and possible approaches to solving some of these congestion issues. So this one, people are calling load-aware packet spraying, and it's a little bit like ECMP in the sense that you're distributing your data on multiple paths. But what's done here is that there's a feedback from the load end talking about that's able to assess the congestion and feed it back to the source. And then the data is sent not on a single path, but on multiple paths. So you have some basis of something less than a flow. It could be a packet by packet basis. But because your data is sent on multiple paths, you'd have to do, you'd have a reordering problem because the packets could come out of order, so they have to be sequenced in some way. But that's a possible way to deal with a more fine-grained granularity of the ACMP kind of approach. And another one that we discussed in the paper we called push and pull hybrid scheduling. And the basic idea here is that in the congested scenario, you can look at cases where where it's referred to as request grant. It's a little bit confusing in a sense because it's not the way you'd look at requests and grants in, for example, a wireless system or some kind of system like that. But essentially it's giving the opportunity for the receiver to provide an indication to the sender when it's time to send and let it be able to send. And that's what's referred to as pull scheduling. And then this push and pull hybrid enables a kind of a transition from fully push data, which just sends it and assumes it's going to be getting there until it gets an ACK, and then the heavy load where the data is